you so much for the invitation to be here. It's a great honor. Okay, so overall, I guess, okay, it's fabulous to have these 6 lectures, all quite substantial, and it's very nice to sort of have enough time to be able to say something. And also, it's a big subject, and it's not possible to say everything. And so, I guess the overall thing is, I would kind of like to go from I would like to describe generally what's been happening in the area over the last 5-ish years. And I also would like to kind of get to more recent topics of interest. And but I don't have I would say I'm not super committed to any agenda. There's different possible choices to make about which way to go. And so getting feedback from people is great. If you want to ask questions, questions are wonderful. And if there are things people want to hear, then tell me after the lecture, and I'll try to do them this week, well, these weeks. Okay, so I guess today I want to start with a kind of general overview of the geometric Langlands conjecture and correspondence, and kind of do a little bit of orientation on some of the things that I'm going to want to talk about. So the setup is the following. So yeah, and I guess also people. If I say things, and again, questions are great. So if I say things that don't make sense, just ask. So the setup is X, a smooth projective curve over some kind of field K, and G, a reductive group. So let's say for me, reductive always means split and connected. And then I'm going to take G check to be the Langlands dual group. I guess I'll say more about this in just a second. And the other thing I fix is a theory of sheaves. So I can write, sheaves on, let's say sheaves for varieties and schemes and stacks over this field K. And these are always going to take values with coefficients in some kind of field that I'm always going to call E. And this is going to be a field of characteristic 0. So just to have examples in mind for what I mean by sheaves. So concretely, so there's the sort of de Rham setting. So here, my K is a field of characteristic 0. My E is equal to K. And by sheaves on some space Y, I mean the category of D modules on Y. So essentially, in the case when Y is, let's say, is smooth affine variety, this is just, or smooth variety, this is just a quasi-coherent sheaf on Y with a connection, algebraic flat connection. Another example is when K is equal to C, and E is any field containing Q, for example, Q. Then I can take sheaves on Y to be, for example, constructible sort of Betty sheaves. So I take the complex points of Y, I give it the kind of analytic topology, like the I'm just writing that because it's some transcendental thing, but just like the usual topology. And I consider constructible sheaves on this space. And sometimes it's convenient to say that this is contained inside of sheaves all of Y, which is all Betti sheaves, not necessarily constructible. And let's say, yeah. OK, by constructible, I really mean weakly constructible, and I also allow colimits of these things. So, OK, that was more technical than I wanted to be. Just some words for specialists. And then the last example that I will want to care about is K is arbitrary. E is going to be QL bar for L invertible in K, prime, well, L is prime, and coprime to the characteristic. So, and then I take sheaves to be étale sheaves. OK, so these are the kind of three sheaf theoretic settings that I have in mind generally. And geometric Langlands sort of plays out in different ways depending on which one you take. And the relationships between the different versions of geometric Langlands is one of the sort of, I think, really, so I would say the relationships between these different forms of geometric Langlands is sort of a big, important recent theme. So then in this case, so what we form is bun G. So this is the stack of G bundles on X. And then the main object of study is sheaves on bun G, maybe certain sheaves on bun G in practice, but let's say at first approximation it's sheaves on bun G, and then inside of so I don't just want to study this category. I want to study, well, let me just want to say what the basic kind of objects of study in this category are, and what kinds of things we're looking at here, and that will be discussed more over the series of lectures. So the first thing is that this has what are called Hecke symmetries, and then the next thing is that there are sort of various classes of objects. It's not as weird as I thought. OK, the objects have different names. So they're sort of Whittaker kind of style objects. They're Eisenstein style objects. And then the third is Kac-Moody sort of localized objects. And this is special to the de Rham setting. And so generally speaking, what geometric Langlands is about kind of understanding this category of sheaves with its Hecke symmetries and the relationships between these Whittaker, Eisenstein, and Kac-Moody localized objects. So and the relationships between each of these three classes with the Hecke symmetries. So this is kind of the package, and what I want to do is be unwinding this package. Okay, any questions at this point?
Actually, those sheaves, there are also some Higgs sheaves.
I don't. So yeah, I don't. Yeah. Other questions? I mean, yeah. there are certain extra structures you could consider, like Hodge module structures and so on, but kind of it's usually difficult to find interesting phenomena somehow when you do that. Hard for me. Okay, so other questions? Okay, so now I guess I just want to get the various versions of the geometric Langlands conjecture on the board. So the first is the sort of most classical one, which is due to Beilinson and Drinfeld. The sort of correction by this refinement by, well, maybe let me say first a little, just a bit of, let me say some slight words about motivation. So what the Langlands philosophy says it says that there's a connection between some kind of automorphic forms and some kind of, and this is automorphic forms, so this sort of depends on G. And automorphic forms, let me say, they also depend on, for example, a choice of global field, and the global field is encoded by the curve x here. And then these are supposed to be corresponding to some kind of representations of something like a Galois group of your global field into this group G check. And there's sort of many there are many unsatisfying or many challenges in turning this into something more precise. So there's supposed to be so for me there are various mysteries here. So one of them is what kind of Galois group. Another is what sort of correspondence exactly do you expect? And then there are also sort of maybe some kind of technical points, which is that there's sort of, if you try to think too naively about a correspondence here in different formulations, then you run into things like kind of, there's this Arthur multiplicity formula that sort of corrects maybe some kind of naive expectations that you might have. And yeah, so I just sort of want to have that as kind of a general framework. And then I want to advertise that sort of one nice feature of the geometric Langlands theory is that you have sort of we sort of really have kind of best hope conjectures, well, and theorems in the global setting. And there are many deficiencies also, and it's a technical subject in a lot of ways. But I sort of want to just maybe highlight this as sort of one piece of motivation. So the idea here is that, which probably many people have seen. So, well, let me just say it very briefly, and then I can say more if you want. So the idea is that this category of sheaves on bun G plays the role of unramified automorphic functions. And this is some kind of, via some standard analogies in geometric representation theory. And and so the goal, and then the role of this Galois group is going to be played by some kind of suitable fundamental group. So and let me put Galois a little bit in quotes because it's sort of, there's this approximately symbol, and there's sort of a long story about what kind of expectations you should have for this sort of object that goes here. Yeah, so now let me kind of just get on the board sort of various forms of the geometric Langlands correspondence. So the first is due to, like I was saying before, Beilinson and Drinfeld, with this correction due to Rankin and Gatesgory. And it says that the category of D modules on, so this is the de Rham version, category of D modules on Bun-G is equivalent to some kind of coherent sheaves with nilpotent singular support. So it's a whole mouthful. I'll say what these words mean in a little bit. On Loxis G check de Rham, so here Loxis G check de Rham is equal to the moduli of G check bundles with connection on X. I don't know, for people who like a lot of formalism, this is the stack of maps from X de Rham into BG check. It's like one way to write it for people who like those kinds of formulas. Just put it in parentheses. So let me just say one word about this. About the geometry of the stack for a moment. So this moduli space of local systems, so this maps down to this this Bun-G, and then there are various fibers here, just to give a feeling. So if you have a G bundle, then the fiber is going to be the space of connections on PG, which is equal to either an empty set or a torsor for global sections of the corresponding adjoint bundle, tensor with one forms. And as a technical comment, this stack, so it's just to give a little bit of a feeling, like this is some kind of very nicely behaved moduli stack. So, and in fact, it's even more nicely behaved than Bun-G in the sense that it's quasi-compact. So this Bun-G is somehow a very large object. It has this sort of big, it's a union of many, many opens, this sort of Harder-Nar-Simhan stratification. And for sort of most terms in that Harder-Nar-Simhan stratification, they don't admit any connections. And so this doesn't talk to somehow many of the bad things about this space. And then there's this mouthful of Indco Nilp, and let me just kind of hold off on that for just a moment. Maybe let me, I meant to say one other thing about it. So, okay, I'll put it up here. So this has a quotient functor onto Loxis G check. And this quotient functor, it's not an equivalence, but it's sort of, let me say it's not super far from an equivalence. And the kind of general idea here is that if you took the Langlands philosophy a little bit naively, then you would say that these two categories are supposed to be equivalent to each other. And this is supposed to be kind of like a Arthur multiplicity formula style correction. And I guess I would like to ideally say more about that by the end of these lectures. OK, questions at this stage?
I think this example is kind of single. It's very big categories equivalence. You don't speak about harmonic models at all.
Right.
Yeah, because the less would be very different size.
Yeah. Yeah. So that's right, and that motivates the next thing I'm going to say. OK, so there are sort of these other variants. So the next one is due to Bensby and Nadler. And this is what we call Betty geometric Langlands. And it says the following. So what we'll do is we'll take Loxis G-check Betty to be just sort of the character stack. So this is, if you like, it's like the stack of Betty local systems on X, or X of C analytic maybe. And so suitably understood, this is the stack of maps from the just sort of usual fundamental group of X into G-check modulo the conjugation action of G-check. And let me just say, you need more care in the case when X is equal to P1, just somehow there's like a lot of derived structures that go on here. And let me just kind of comment that all other curves are k pi 1s, so the fundamental group is a good object. And yeah.
But there's still some derived structure for any genus.
There's still a derived structure for any genus, that's right, but for me that's sort of built into the definitions always. Like, and I guess I just sort of want to say, like, when I so like if you want, you could say like X Betty equals like the homotopy type of X of C with the analytic topology, and then this Loxis G-check Betty, it's given just like over here. It's sort of the space of maps from this like this homotopy type into BG check. It's given by the same sort of formula, and I'm just sort of saying if you treat this like the classifying space of a group, which it is outside of the case when X is equal to P1, then you would interpret the formula in this way. And otherwise, you sort of need to account for sort of pi 2. Yeah, so the derived structure is always there, but sort of, if you interpret these things in the derived way, well, first of all, the derived structure is not always there. So if the group is semi-simple and the genus is at least 2, you don't have to worry about the derived structures. And well, in theory, you don't have to worry about them. And but that's not the issue I'm worried about. It's more like if you interpret this in the language of derived algebraic geometry, you'll get a slightly wrong answer. So you should sort of replace this more by like a fundamental groupoid in the case of P1 specifically. Okay, so that's kind of the spectral side of the equivalence in this case. And what they say is that you take the category of you take some category of sheaves, and well, I guess I normalized my notation before a little weirdly. And then they say that this is going to be equivalent to the same sort of formula so what is this category? So I'll say more about this category later. In sort of simple terms later. But the official definition is that these are again sort of weakly constructible sheaves with Kashiwara, Shapira, singular support contained inside of what's called the global nilpotent cone inside of the cotangent space to Bungie. So there's sort of this nilp, and this is kind of some sort of nilp in a Higgs bundle sense, and this is some sort of nilp in a kind of local system sense. And they're a little bit different flavors, but this conjecture has the sort of, at the level of symbols, it's sort of, there's something very pleasant about it. And so these objects are all at least like weakly constructible objects. And you run into kind of, like you could, I think different people have very different mindsets about these things. So when I talk about weakly constructible things, like maybe this bungee is something like the Jacobian, and I can sort of push forward the constant sheaf from the universal cover of the Jacobian down to the Jacobian. So that's like, that's an infinite rank local system. And I think some algebraic geometers find that kind of object to be kind of pathological because it doesn't have a corresponding object inside of these D modules on Bungie. So Riemann-Hilbert compares vector bundles with connection to finite rank local systems. And infinite rank local systems are kind of out of reach for algebraic geometry. And so this category allows those are the sort of corresponding pathological objects, so to say, if non-holonomic things are the pathological objects here.
This kind of like mirror symmetry statement has this in some A model category B model.
Yeah. I mean what like I think the sort of picture that people are supposed to have is that there's sort of like two four-dimensional theories here, and there's sort of an A model, which is sort of equivalent to some B model in the four-dimensional theories, and that when you compactify this along like this Riemann surface, then you get two two-dimensional theories, and the equivalence between the two-dimensional theories is sort of mirror symmetry for cotangent spaces of Bungie and Bungie check. And so yeah, it's kind of like the just bare equivalence of categories in this form or this form you can think of as mirror symmetry, but you can like, let me just say that sort of misses some amount of structure that's not present in general, I would say, in the general mirror symmetry formalism, which is that kind of both of these categories really talk to the curve X, and that's related to this theory of Hecke symmetries. So this general theory of Hecke symmetries doesn't would be sort of invisible, and that's sort of remembering that it came from 4D in some sense. Other questions, comments? Yeah.
Could you talk later about how, considering the different shifts theory, you learn something more in geometric Langlands? Because it seems like you guys are always working in the Durham setting, and like what is interesting by considering also Betty or Etal?
What is what?
You say in the beginning that considering all the different shifts theory, give you something more.
Yeah.
So could you talk more about this?
Yes, I would very much like to do this. Yep, absolutely.
Thank you.
Sorry, since you mentioned Rossi integrated form,
Yeah.
the actual status of the geometric Langlands does imply the existence of a Fourier-type parallel between the derived category of Fourier sheaf on its moduli space for the group G and the Langlands dual.
Not as no. Yeah, exactly. You're asking about the Higgs moduli space. I would not say that that's known right now. I'm not even sure exactly what kind of object it should be because yeah. Other questions, comments?
Also, you said that like if it's not stable enough, like related to Harder-Narasimhan, you have a characterization of when your G bundle has a flat connection. Mm-hmm. What is it precisely?
Like when does a G bundle have a connection? Yes. Let me say it for GLN just because it's. Okay, I can probably say it for G also. So the statement for GLN is that if you have a vector bundle and you write it as a direct sum of other vector bundles, then you want each of the sum, or maybe you write it as a direct sum of indecomposable bundles. You want each of those indecomposable bundles to have degree 0. So yeah, and the I think the general statement is that whenever you have if you have this G bundle and you have a reduction down to a levy, then like, what do I say? So that you can take the degree of that sort of reduced bundle. That's going to be an element inside of pi1 of the levy, and then which is some abelian group, and I want that class to be torsion. So that's sort of the. So in other words, if you go to pi1 of the levy tensor Q, you have to be a little bit careful about that. Then it's 0.
Actually, this example again, very big categories, not maybe like what you will see afterwards, yeah, but it's kind of like half of functional half of what in the first example. It's really huge categories. This is before we get, in a sense, Fourier marquet transform little quantized variety of the same dimension. Mm-hmm. You get like in abelian case representations of 3 abelian percent generations, the same as models of floral polynomials, stuff like this. And, yeah, but very big models and nothing about actual construction.
Correct. And once again, you've given me.
And I'm afraid the rest will be much smaller categories. Yeah.
Yep, that's exactly right. Yeah. So the third example is much smaller categories. Yeah. Yeah, and again, I'm black boxing what this indico nilp is, but it's exactly the same sort of structure here, where this quotient has this quotient, which is quasi-coherent sheaves, and this functor is not an equivalence, but not too far from an equivalence. And I'll, like I said, I promised I would say more about that later. And then the third example, so it's due to us, I guess, which is this. So this is the étale geometric Langlands correspondence, and this is due to me. Which, okay, henceforth is AGK RRV. So it's a series of works with Arinkin, Gates, Gori, Kazdan, Rosenblum, and Varshavsky. And and I'm going to say more about what these works do as I go along. Somehow, the ideas from this project, I think, are something I want to talk about a lot. But let me just give the flavor. So here I work with étale sheaves. Or I can also work with holonomic D-modules, or constructible. So this is sort of like not weakly constructible Betty sheaves. So the point is I work with some kind of like small objects, some sort of honestly constructible objects. Let me just make a technical comment for people who haven't like spent a lot of time in the Betty world, that weakly constructible like sheaves, they include these infinite rank local systems. So if you think about a local system as a representation of the fundamental group, or as maybe a module over the group algebra of the fundamental group, it's the question of, do you allow finite dimensional modules only, or do you allow infinite dimensional modules? For example, does the group algebra itself count as a local system? So that so weakly constructible allows the group algebra. Constructible means finite dimensional fibers. And always here, I really mean ind. I allow ind in all of my categories, but these are like the sort of generating objects. So in this case, we defined a space. It makes sense for any group H. A space that we call loxis restricted. And this is the moduli space of, so it has a simple description, actually. This is the moduli space of, okay, there's sort of this right T exactness. This is something that normal people would ignore, but it's just because I really work with derived categories. My brain's a little rotten that I want to say this. So the moduli space of right T exact symmetric monoidal functors from this rep H into these sheaves on X. And let me just make some kind of comment here. So if you take, more precisely, so you're just sort of filling in some of those details. So when I write these sheaves on X, this is going to be the subcategory of sheaves of X consisting of all objects. Usually I'll call it sigma, with the property that each of the cohomology, let's say each of the perverse or constructible cohomology sheaves of sigma is a colimit of necessarily finite rank these sheaves. These sheaves, meaning, so these are also known as local systems. So I use the words local system and Lee's sheaf more or less interchangeably. I don't really use them interchangeably, but I can't really explain how I use them differently. So it's just it's a thing about context, and the words mean the same thing. Okay, so this is the category of Lee's sheaves, and then by definition, a map from S into this category, the space of H local systems. So if this S is spec A, then a map from S into this moduli space is by definition a map, a symmetric monoidal functor okay, I guess I'm going over here. F from rep H into this category of Lees sheaves on X, and then tensor this category of A modules, aka quasi-coherent sheaves on S. And this is just the category of A modules inside of these Lees sheaves on X. I should say right T exact. So what do these things look like? So I have some kind of big category here because I allow, for example, a direct sum of infinitely many copies of the constant sheaf. That does count as an object here, but it's not the kind of like bad objects I was talking about over there. So I can't see something like in the case of X being GM or something like that, I don't allow like the group algebra of Z doesn't correspond to an object here.
Sorry, what's the assumption on the base field K and the coefficient field E?
Okay, so what I really have in mind here is the world of étale sheaves. And so in the case of étale sheaves, it's the field K should be algebraically closed. Maybe I didn't write that before. And then the coefficient field is QL bar, L's invertible in K. Does that answer your question? Yeah. But I also allow this world of D modules where K doesn't have to be algebraically closed, or I allow this Betty world, but sort of constructible in both cases.
So in the étale case, K is any characteristic.
K is any characteristic, so I allow positive characteristic in particular. Yeah, so okay, so I just sort of want to say I allow certain sorts of big objects. So there are some kind of tautological objects in here. For example, if you just take like a usual Lees sheaf, like QL bar, like the constant sheaf, then you're allowed to just tensor that with A. That's a direct sum of infinitely many copies of that constant sheaf, and it counts as an object inside of here. So like I sort of have these objects which are free in the A direction, but I don't have objects which are like free in the fundamental group direction. I only have things which are kind of, well, finite dimensional representations in the fundamental group direction. But kind of here, this is some nice symmetric monoidal category. Basically, it mixes tensoring A modules and tensoring Lees sheaves in the sense you know both of them. So it's really not we write, I guess in the papers, we always write these formulas with tensor products, and I just sort of want to emphasize that like this tensor product of categories is really essential for working with this stuff, but just to make sense of this definition, you really don't, there's nothing like really that sophisticated that's going into it. What do I want to say? So I guess I sort of want to just say very brief comments about the geometry. So this Loxus H restricted is a disjoint union of some components, infinitely many components, and here this sigma is going to be, so I'm going to write the words a little bit, like for general groups you should spell out what you mean by this, but this is an equivalence class under conjugacy of semi-simple H local systems. So for example, every irreducible local system sits in its own connected component, the connected component is like this connected component is essentially a formal moduli problem. That's not exactly right, but it's basically a formal moduli problem. And the only sort of physical directions are nilpotent, but there are some sort of stacky directions as well. Well, in principle, and so it's basically just this is sort of the this is basically a stacky version of the deformation space of the irreducible local system, and so it's something like pretty familiar to some people. In the other components, I'm allowed to just sort of do very simple operations. Like if you give me a non-semi-simple local system, maybe it's an extension of one local system by another, then I can sort of bare scale it down to the semi-simple local system. And that's a sort of genuine physical direction inside of this the stack. Or I could move within the space of extensions. And those are some genuinely physical directions, but that's the only sort of physical directions that I have here. So this is somehow like sort of for what Maxime was saying, this is like, I'm sort of making the, well, let me write the, no, okay, I guess I can erase this. So in this case, what the conjecture says is that the category of sheaves with nilpotent singular support on bun G is going to be equivalent to again, this endco nilp of loxis G check restricted in a way that, of course, satisfies many compatibilities. And here, this is singular support as defined by Balanson. And let me say, again, I'll give a different notion, well, for étale sheaves. I'll give a different description of this category, like I said, later on. And just sort of want the symbols on the board for now. And so here, sort of to get to Maxine's point, so here the objects are kind of much simpler. I don't really have pathological objects in this category anymore, in the sense that there's nothing which is sort of genuinely infinite rank. There's nothing that's genuinely non-holonomic. In fact, in the world of D modules, everything that's here is regular singular. So it's kind of a very it's a very conventional kind of sheaves. These are like the most conventional sorts of sheaves you can consider, but it comes at the expense. The confusing thing about it, and the reason maybe it happened third, is that this moduli space is more pathological. And so, there's always sort of this problem that if you have an étale local system, well, that there's kind of clearly no like less, like you can sort of dream of a moduli space of étale local systems, and it doesn't, you run into issues if you try to like run it at all, unless like if you wanted it to be, for example, connected or not so far from connected. And so kind of the job of this space is just like the idea of this space, the thing that was psychologically difficult is just to say, it's fine if all of these local systems are in different components. It doesn't, you actually just can kind of proceed. So you don't need to be able to deform one irreducible local system into another irreducible local system in order to get the theory off the ground.
So for instance, if G is GLN, is it possible to describe each of these connected components using some quivers, the X quivers, this kind of thing?
These connected components? I wouldn't say quivers. I would just say you take the fundamental, like the étale fundamental group of your curve. Again, this is over algebraically closed field, so it's basically a surface group, maybe some kind of pro-finite completion of it's a quotient of a pro-finite completion of a surface group. And then you look at representations into GLN, And then I take all of those, and then I impose an equivalence relation where, first of all, for every representation, I identify it under this equivalence relation with its semi-simplification. And and I also work up to conjugacy, of course. And that's what the components are indexed by. So, yeah, it's not like there's no like combinatorics or something.
So once you fix each simple factor, then you're looking at all the possible extensions between these.
Yeah, exactly. Yep. And so kind of like I would say that like the general idea here is that like if you have sort of sigma 1 and sigma 2 which are like irreducible, then it's not really, you might kind of want to draw a path from sigma 1 to sigma 2, and this is like a bad idea. Don't try and do this. But the sorts of things that you might do are that like you might have various extensions like this. And so this is sort of some x1 of like this, which is some kind of h1 of, sorry, x1 of sigma 2 into sigma 1, which is h1 of sigma 2 dual tensor sigma 1. And maybe this is like some kind of étale cohomology. And so this is like a perfectly good vector space over QL bar. And so that really does have some kind of physical directions. And that's the sort of, those are the only sorts of physical directions that we see in a sort of precise sense. So that's all that's going on. So it's something which is like, it seems like it should be really complicated, and it's not. It's just, yeah. Yeah, and maybe I should say that all of these components are sort of ind affine. They're formal schemes, mod a group. So I can say this better. Each component is a formal scheme modulo H. So that's the sort of coarse geometry of this space. So formal scheme, basically it looks like the formal completion inside of like the true moduli space of local systems is kind of what you should think, but there's no true moduli space in the étale world. That's a precise statement in the Drum or Betty world. So. Other questions? Okay, so those are sort of the those are the statements, and now I sort of want to, I guess, start digging in on them a little bit more. Well, okay. So I want to fill in some of the gaps of what I said. So, so one question is, what is this indco nope? And let me just, I want to give a working description of it. So, okay, so here I want to keep this discussion pretty brief, and so I'll try to say everything as efficiently as possible. And it's going to make the notation seem weird, but it's a definition. So, okay, so how should I say? So classically, if you take like, say like A is a Noetherian ring, for example. If I take the abelian category of A modules, then this is ind of co of, let me just say A. So this is finitely generated A modules. So this ind means the ind category. So there's some general construction that kind of takes a small category and produces a big category. And sort of you think of objects here as kind of formal co-limits of objects in the small category. And I'm saying every A module, just like, so this, sorry, So heart means the abelian category of A modules. So the every like just when you take commutative algebra, every module over a Noetherian ring is a union of, well, over any ring is the union of the finitely generated submodules inside of it. But here this is sort of a nice abelian category. And then derivedly, there's a sort of slightly different statement, which is that the derived category of A modules is end of perfect A modules. So these are perfect complexes of A modules. So basically, you take the ring A itself, you just do all the finitary operations you know inside of the derived category, and then you get this class of perfect modules. And this category of A modules is the end completion of that category. So this is sort of, it's like a very parallel statement. These coherent modules are kind of, it's again the same thing where you take like finitely generated, you take A as a module and you start doing things like taking direct sums, or maybe taking co-kernels, and that gives you the class of finitely generated A modules. So these are sort of very parallel statements. But there's a different thing you can consider. There's somehow this like confusing point, which is that this isn't really the derived analog of this statement. So you can also consider co of A, and so this is going to be the set of complexes, let's say bounded complexes with finitely generated cohomologies, and you can also consider end of co of A, and usually we just abbreviate this to end co of A. And if you stare at this category, or usually A is commutative and we say spec A instead. And so this is kind of what should be on the derived side of this statement. I hope that's kind of clear. And there's kind of a subtle difference between these two things. So this co of A always contains perf of A. And so, well, if you work with DG rings, you have to be slightly, it's not exactly true necessarily, but let me for the discussion we're having, I don't need to do that. So this perf of A is contained inside of co of A, and so this implies that sort of A mod is always going to be contained inside of this end of co of A. And then also, co of A is contained inside of A mod. So that implies that I get a functor. Yeah, I should say this is contained inside of here, and Sarah says that this is an equivalence if and only if A is regular. In other words, spec A is sort of smooth. I guess now I'm maybe assuming A is commutative. And so, okay, so now I have this end of co of A. Well, I guess I'm about to write this. And I obtain an induced functor from here to here that I might think was an equivalence based on what's happening over there, especially because this is contained inside of this, and so what's really the difference? And so the kind of the fact, which is sort of just proved by almost staring at this equivalence of abelian categories, is that what's happening here is the following. So I'll call this functor C and this functor Xi. So what's happening is that this ind of co of A is mapping via C, and it goes down to this category of A modules. It has this fully faithful left adjoint, which then forces the right adjoint to be a quotient functor. And there exists a unique T structure. So C is T exact, and an equivalence on plus categories. And kind of the claim is that that explains all of the features that we were seeing. So these two have the same underlying abelian category. In fact, they have the same underlying bounded below derived category. This one is a little bit bigger than this one. But it's bigger in a way that's sort of only happening at the level of unbounded derived categories. And so that's like the sort of brief summary of mind-bending commutative algebra. But I just sort of want to say that the passing from one of these to another, it's sort of like, it's a serious point. They're different categories. And also, it's not like, there's sort of this choice about working with big categories and with small categories. And so there's sort of this world where, like, if I think about like A mod and int co, then I'm thinking about perf versus co. But so I mean, so this is something that feels more concrete to many people. But also, this co is contained back inside of A mod. So I sort of could have reconstructed the entire story from this category of A modules, just maybe thinking about the T structure a little bit. And so there's sort of this circle where, like, I guess I'm trying to say that like int co is bigger than A mod and co is bigger than perf, but actually also A mod is bigger than co, and that's then sufficient to sort of reconstruct this int co. And so there's these sorts of homological algebra games that we'll also get into at some point. Questions about that in a moment? And I guess I want to say, for people who think about like automorphic forms and things, for me this kind of like particular like sort of functional analysis, like this brand of subtlety in homological algebra, it's like it's something which is unique to the categorical world. It doesn't really have an analog in just pure function theory, and it's something which I think is very like powerful in the geometric theory. So I hope to explain. It's one of the real advantages of, so to say, geometrization. Okay, so now, so this int co nilp, well, I guess I should say int co on some kind of space of local systems. So this kind of can have any superscript you want here. So this is going to be contained inside of this int co on locsys g check. So I now cheating slightly, but it just all of the words made sense in the non-affine situation as well. And it's something which is sort of wedged between quasi-coherent sheaves and int coherent sheaves. And so let me just say what the description is. So I'm going to define, so for every parabolic with a Levy quotient M check. So what I do is form the following sort of basic diagram. So I take this locus P check, and it maps to locus G check, and it maps to locus M check, and this I'll call P, and this I'll call Q. And so what is this diagram expressing? This is saying, like, you might consider sort of reducible local systems, say for GLN. So those are sort of representations that go into some parabolic. So yeah, it's sort of some block matrices with some stuff up in the upper right. And that's what a local system for the parabolic is. And then I can take the induced, maybe semi-simple M-check local system, or I can take the induced G-check local system. And so that's like the kind of construction we were talking about before about sort of thinking about reducible local systems. So reducible local systems are just ones that lift to locus for some parabolic. And so then we, and maybe I should say, this map is proper. So all of the fibers you can see will be contained inside of the corresponding flag variety for, or at least twisted forms of the flag variety G check mod P check. And this map, let me say, has finite Tor amplitude for people who are careful about those things. So so then what we do is we define the functor of spectral Eisenstein series. Well, I could write other descriptions, but well, okay, there are various choices here that don't really make it a difference, but let's say for now, okay, so as the functor Q upper star, P lower star from quasi-co of locus M check to quasi-co of locus G check. And so now if you have a perfect complex on this locus M check, and I apply this operation, so Q star of F is an element of this perf of locus P check. And that's by this finite Tor amplitude. So sometimes you do pullbacks and you get things which are unbounded from below, but not in this case. And then I can form this P lower star of Q upper star of F. And just what algebraic geometry tells you is that this is a coherent sheaf on locus G check, but it's not necessarily it's not necessarily here in general. And so then I'm going to take co-nope of this locus G check to equal the subcategory generated by this sort of spectral Eisenstein series of perf of locus M check for every, well, P check. So let me just say,
even though this push forward is just a coherent sheaf, coherent complex, this Q resulting spectral Eisenstein functor lands into the cross-coherent category. Mm-hmm. Okay.
So yeah, so this co-nope, I'm saying, so this is the subcategory, let's say, of co on locus G check, just generated by these objects.
Sorry, I'm confused with the one before. You defined the spectral Eisenstein functor to be this by this formula.
Yeah.
And it lands into QCO.
It lands into QCO, but yeah, it lands into QCO, but I'm saying the following. So if you have a push forward along a proper map, it sends coherent sheaves to coherent complexes, right? So it sends coherent complexes to coherent complexes. And so what happens here is I take this F, I pull it back to here, I get a perfect complex, so basically O. And then I do this push forward down here, and yeah, a priori I get a quasi-coherent sheaf, but just what algebra, like again, it's because this P is proper.
Yeah.
So it sends, so like this is contained inside of coherent sheaves on Loxis P check. Does it answer your question?
Yes, I'm just confused.
No, it's good. It's I appreciate it. It's confusing stuff. So let me just say, when G check is equal to P check, this is just saying that by design, perf of Loxis G check is contained inside of this conulp Loxis G check, which now is some subcategory here. And so, yeah, so again, the statement is there's this ind conulp, which is a mouthful, but what it really means is I take perfect complexes on Loxis G check, and I also take perfect complexes on every levy, and then I parabolically induce those perfect complexes. And the sad fact of life is that I get things which are not necessarily, they weren't exactly perfect complexes, they were something marginally worse, in the way that coherent sheaves are marginally worse than perfect complexes. And I don't get all coherent sheaves in that way. That's why I need the mouthful. I just get those that have what's called nilpotent singular support. And why is this called nilpotent singular support? There's a long paper by Raskin and Gatescory about it that I would point you to, but I don't want to get into that discussion. So basically, there's a more geometric description of this construction that's not particular to local systems, and I don't need it. Yeah. Okay. Other questions? So okay, now I've stated most of the versions of geometric Langlands. Let me let me just make a sort of remark on the status. So Duram, Betty are both known. This étal version for when the ground field has characteristic 0 and is sort of almost known for characteristic of k equals p, like, or maybe you could say it's 50% known, or it depends how you want to say it, but what we can prove is that if you replace this Loxis G check restricted by a disjoint union of some of its components. So there's this more technical statement in this last case, and I just sort of don't want anybody to have come away from this discussion thinking thinking otherwise. So there's some. Does it include what? Yeah. Yep. Yeah. For GLN, yeah, for GLN it's okay for everyone, yeah. So I basically, I said that what I said was that these components are indexed by semi-simple local systems. So in particular, there's some levy around, and that semi-simple local system, you can think of it as an irreducible local system into the levy. And then it's a yes or no question. Basically, does there exist a Hecke eigensheaf for that irreducible local system? And that the ones where it's yes, those are the components you see. So in particular, the trivial local system or anything where the semi-simplification is where it's reduced to the Borel, you're okay. Or if the corresponding levy is GLN, you're also okay, or product of GLNs, type A.
Sorry, could you please say what is written?
Sum of its components. Yeah.
But what does it mean? So on the side of Bun-G, there is like a direct sum of the categories, which is equivalent to...
No. So we have full control over like the sort of automorphic to Galois direction. So yeah. So what it means is like this sheaves nulp on Bun-G is equivalent to this indco nulp and this loxis restricted G-check prime is sort of the notation.
And conjecturally, this is the whole loxis?
Conjecturally, this is the whole loxis. Yep, exactly. Yeah, but that's not known at the moment. And what's not known, the specific thing we don't know is if you give me an irreducible G-check local system, I don't know that there exists a Hecke eigensheaf in general. In characteristic B. There are like many explicit constructions of what it should be, and it's hard to show for any of those explicit constructions that what you get is non-zero. And at least I don't know how to do it. Okay, so that's the sort of big picture version of what these various versions of geometric Langlands say. For the most part, I haven't told you what sheaves nulp is. I just sort of wrote it on the board, and I will tell you what it means, but I'll tell you later. Okay, so then what I want to do is start kind of getting more into the actual structures of these automorphic sheaves. I guess I want to comment one thing, which is that maybe a piece of conventional wisdom in the subject is that kind of understanding the space of local systems is usually sort of easy. I mean, like, take that with a grain of salt. There are various things you can, like, that's not always 100% true, but mostly it's kind of true. And that conventionally, what we think is that this category of sheaves on Bun-G is the most difficult part. And so what I explain is sort of how do we start probing it. Okay, questions before I go on? Yeah, and well, maybe I should have also said the words that one reason I really care about this version for characteristic P, of course, is that this is where we can really talk about relationships to honest automorphic forms and the sort of actual Langlands program.
Actually, your K is algebraically closed.
My K is algebraically closed in the étal setting.
But you can add the Frobenius in characteristic P.
Right.
You can get statements for.
Yeah, we can get statements with the Frobenius also. Yep, and so that's one of the things that will happen over the course of the 6 lectures for sure. Is that process of like decategorification, so to say, which involves adding the Frobenius on the spectral side. Other statements? Other questions? Also statements are great. Okay, so now I want to start talking about the Hecke symmetries. Okay, so okay, so I guess, well, many people will have seen this before. So there may be 2 things to know offhand. So what is this about? So the most basic version of these Hecke symmetries states that whenever you have a point in the curve, which for number theorists is the analog of a prime number, and you have a representation of this Langlands dual group, then there's a corresponding Hecke functor from sheaves on bun G to sheaves on bun G. And this involves modifying G bundles at a point. So in the case of, not just at a point, but at x. So this is supposed to be the kind of basic geometric picture you're supposed to have in mind. And so let me just comment that very, very, very classically, when you think about line bundles on curves, you always want to write them as O of a divisor, and then kind of maybe prove the independence of that choice for some given problem. And writing it as O of a divisor, you can sort of think of that as doing some like iterated, simple modifications of O at different points. And so this idea of sort of Hecke symmetries in general, it's in some sense, it's just a more sophisticated version of that like most elementary thing that you do when studying line bundles in the theory of Riemann surfaces. And so let me first give an example. So when G is GLN and V is equal to the standard representation, so then what you do is you form the following moduli space. So there's bun GLN, there's bun GLN, and what you do is you take the set of embeddings, the set of pairs of bundles of rank n. I take E embedded into E prime, and then I ask that that also be embedded inside of, well, let me just even say it as E prime mod E is a length 1 torsion sheaf. Supported at x. So in other words, it's isomorphic to the skyscraper sheaf at x. And so here, so let me just to give a little bit of a feeling. So for people who haven't thought about these things before, so like that's going to force that E prime is contained inside of E of x, and the data of E prime is then equivalent to the data of a line inside of the projective space for E of x mod E, where this line is going to be E prime mod E. So this quotient is, OK, it's clear. So the fibers of this map look like projective spaces, and the fibers of this map also look like projective spaces. And projective spaces of dimension n-1. So in the case of GL1, both these maps are isomorphisms. But in the case of higher GLN, then there's sort of this space of possible lines that you can choose.
So EX is a torsion by OX? Or EX is a torsion of E by OX?
Wait, say it again?
EX, E parentheses.
Yeah, EX is, yeah, sorry. E of x is E tensor with O of x. Yeah. And so the point is like, OK, think of like O plus O. Then this is O of x plus O of x. And when you do the quotient, you get a 2-dimensional space. That's all I'm saying. So you get this 1-dimensional space of possible modifications, this P1 of possible modifications. Other questions? So then the corresponding Hecke functor is just given by doing, so OK, there are these two projections corresponding to E and E prime. And wait, I did this wrong. Left and right. So this is somehow the notation. And the corresponding Hecke functor is that I do the pullback along the left projection, and I write upper shriek, but it doesn't make a difference because of it's basically a fibration. So so I just so this is the standard representation. This is at my point x. I have a sheaf f. So here f is some kind of sheaf von Bungee. And I have the habit of liking upper shriek and lower star functors, and so I'm going to write it in those terms. But and there's a shift that goes here that I'm going to ignore. But just what this is saying is you just kind of, well, if you imagine this automorphic sheaf, so this is something, it's sort of like an automorphic function. So an automorphic function would assign numbers to vector bundles. What I do instead is I assign vector spaces to vector bundles. And now what I would want to say in automorphic form language is I just create a new automorphic function by sending sort of e prime to the sum of my automorphic function over all possible modifications like this. That's what the Hecke functor is doing. But instead I consider, instead of saying sum, I do cohomology. So that's what this lower star is doing. So I consider kind of the fiber of my my Hecke modified f is the cohomology over the space of all such modifications, taking the fiber at this point instead. Questions about that? So in general, here's what I do. So I'm going to take what I call the global Hecke stack, and it's going to be a little bit more pathological. So okay, what's the problem? So the problem is that here I said like take an embedding of vector bundles, but I don't know what an embedding of G bundles is. And so I'm going to say just kind of the thing I can say. So I'll take two G bundles plus an isomorphism when I puncture at this point. So I just look at all the possible ways of modifying my my bundle at this point. So I don't say that it has to be a simple modification. I just say that they're isomorph. So I could, like in this world of vector bundles, I allow things where E is contained inside of E prime is contained inside of E of like maybe 100 times X. I allow poles of order 100. Or maybe the inclusion goes the other way. I just ask that they're isomorphic. Basically, well, E prime should be contained inside of some sufficiently large twist of E, and E should be contained inside of some sufficiently large twist of E prime. And so this is something which is like an end algebraic stack. It's a little bit worse. And now this has a map down to what we call the local Hecke stack. And so that's just sort of looking at the type of the modification. So here, I produce something which is much too big in order to recover this earlier construction. So I have to be able to recover this earlier construction. And sort of note that what I did here was I sort of picked out some family of modifications in some way. And that sort of the sorts of modifications I was saying only involved what was happening near the point. And so I want to be able to express like, what are the types of possible modifications? So what I'll do is I'll look at the local Hecke stack. And these are going to be G bundles on the formal disk. Well, spec of sort of. I take another G bundle on the disk, and then plus an isomorphism on the puncture disk, which is this spec of K-Laurent series Tx. So Tx is a uniformizer at the point. And now this geometric Satake equivalence, it gives rise to a very nice functor from representations of this dual group onto these sheaves on this local Hecke stack. Maybe I should put the point. Namely, an irreducible representation of highest weight lambda check. Well, maybe let me just say that the points of this Hecke stack, like the k points of this local Hecke stack, correspond to dominant co-weights. And under this equivalence, under this functor, this v lambda check is going to map to the IC sheaf of the closure of the corresponding point. So because this is a stack, points are not closed. But basically, maybe I should say, so the closed points correspond to what are called minuscule co-weights. And so the standard representation for GLN is a minuscule co-weight. And so that tells you that you didn't really run into anything serious about IC sheaves. It was a closed point already. So you didn't. The difficulties of the IC sheaf have to do with the boundary of the point. And so then the corresponding Hecke functor and yeah, I should give this some kind of name. So I'll say V maps to SV. So S for Satake. The corresponding Hecke functor is okay. It'll be this TVX of F again, and it's given by the same sort of formula. So I push forward. First I pull back my F along the left leg. Then I tensor with some kind of weight. So I didn't have to write this formula. I didn't have to write this term before because I sort of had already pinned down a smaller space. So so here I'm going to call this R for sort of restriction to the disk. And so what I do is I take this Satake sheaf. So it's probably supported on some finite dimensional piece inside of this local Hecke stack. And then I just pull it back onto this global Hecke stack to pick out some piece inside of here. And the piece I pick out has some weights on it, or it has some stratification that's like the stratification of the closure of the point. And each of those strata have their sort of different weights, and that's encoded by the fibers of the IC sheaf at those points. But whatever, all I do is just pull back, tensor by that basically IC sheaf, and then push forward.
How does this work in the Betty setting, since you have IC? Like, which sheaf theory are you using?
Well, this works for any sheaf theory.
But for Satake, at least.
But I mean, Satake. Okay, so this space, all of your sheaf theories produce the same answer for it.
But can you take IC sheaves in the Betty setting?
Okay, are you worried about like real constructible versus complex constructible? Okay, so on like a real manifold, you can't generally say what the IC sheaf is, but that's not my situation here. Like, I'm just saying like this.
I'm also worried, like from what I've seen, like you use derived Satake in general, like the infinity version of Bezrukov-Finkelberg. But is this defined for all sheaf?
Okay, so I didn't say anything about derived Satake right now. This is specifically underived Satake. But let me just say, like, this category, like, if you work in the Betty setting, you might have like big sheaves or something. You could consider sheaves all on this Hecke stack. It's some formally defined thing. It's the same as the constructible category, which is also the same as the D-module category, which is also the same as, you know, so it's kind of, it's a little bit hard to screw up that part of it. Yeah. Is it okay? Yeah. Yeah, so like at the level of abelian categories, this functor is an equivalence, but at the level of derived categories, it's not an equivalence, and that's the subject of this derived Satake, is sort of refining this side in order to make this an equivalence. But yeah, I don't need that at this stage. All right, good so far? Other questions? I do want to allow, amazing, great transition, yep.
But you have factorizable Satake for all the shift.
For what?
For all the shift theories also?
Yes.
Like étal factorizable Satake derived. Well, okay, no, not derived, but just it doesn't change anything.
No.
Okay.
Yeah. Yeah, I mean, in some sense, it simplifies things. There's this. There's fewer pathologies you might worry about. Okay, yeah. So now what I want to do is, as everyone's saying, okay. So, well, maybe the first. Okay, so geometric Satake is a rich theory. And I want to tell you what it produces. Okay, so the first thing is that ref G check, it really acts on this category of sheaves on Bun-G when I chose the point. So this is a monoidal category. And here this is the Hecke action at X. So the next thing is that I can move points. So this point x, it's something of geometric nature, and it makes sense to vary it. And so what's the output in this case? So if I have this representation, in this case, I'm going to get a Hecke functor. Maybe I'll TV. Let me emphasize the capital X. And what this is going to do is go from sheaves on Bun-G to sheaves on Bun-G times X. And it's going to have the property that if I take sort of the identity times the inclusion of this point and then pull back to this sheaves on Bun-G, that this is given by this Hecke functor. Just for the fixed point. And the construction is just repeat everything with a moving point. Is it okay? No is an acceptable answer, but okay. So the correspondences I wrote down before all made sense, and geometric Satake thing, it didn't really depend on the choice of point in any essential way. And so, okay, so kind of now I can try to combine 1 and 2 a little bit, and so what happened here? So what I told you here really was that like if you take this tvx and you compose it with twx, that this is equal to t of v tensor w at this point x. And so let me try to consider, well, in particular that I should highlight that the Hecke functors for different representations commute. So now what happens if you try to vary the points? So kind of let me just comment that this the fact that the Hecke functors commute at different points is supposed to be trivial, and I sort of want to express that they commute at different points and that they commute at the same point simultaneously in a nice way, and yeah, also just consider the composition of these Hecke functors. So so the composition now of TV and TW. Wait, which order did I do it? TV plus TW. Now it really maps to sheaves on Bun-G times x times x. Is it clear? So basically I apply this TV, okay, really I would say this as apply TW and then kind of do this TV but times the identity along x. So I'll sort of first go from sheaves on Bun-G to sheaves on Bun-G times x, and then I apply the Hecke functor for W just along this Bun-G to get to x times x. Yeah, and so how should I say? So what features are there here? So so the features are, first, if I understand this in these terms, this is isomorphic to TW composed with TV, I guess composed with swapping the two factors on the x squared. So up to this mild isomorphism between the two things, these two functors are isomorphic. The next feature of these Hecke functors is that, how should I say, if I take this no, that's really kind of, well, this is true, and what's happening is that if you restrict to the diagonal copy of x inside of x squared, this gives rise to the usual commutativity constraint. And if you restrict away from the diagonal, this is the obvious isomorphism. Okay. So those are some constructions, and let me also just say briefly that there's a more general version of this where you allow n tuples also, and there's sort of various coherences that you can sort of start to play with, and I'm going to encode them all in sort of the following summary. So so there's something which is convenient to do here, which is to only discuss actual endofunctors of sheaves on Bun-G, like I sort of did initially, right? So I had those Hecke functors that went from Bun-G to Bun-G. Now I have these functors which go from Bun-G to somewhere else. But I want to remember that these more sophisticated objects exist. And so let me say the construction. So if I'm given I a finite set, and I'm given the following two data. So I'm going to take an I tuple of representations, and I'm going to take, let's say, G, a sheaf on x to the I. So this is, you should think of this as sort of like a measure on this on these powers of the curve. So it's going to tell me sort of how I weight the Hecke functor that I'm going to perform. So I sort of want to do. So yeah, what I'm going to do is form a Hecke functor like this from sheaves on Bun-G to sheaves on Bun-G. The idea being that I'm going to sort of do Hecke functors at all of these points, indexed by these representations, weighted by this G, and then I integrate over that data. And formally, what I'll do is the following. So this V is going to give rise first to the sort of universal TV, which goes from sheaves on Bun-G to sheaves on Bun-G times x to the I. And this basically makes sense for this finite set of representations because of a souped up version of what I was saying about the commutativity there. And so then I pull back G. So, okay. So this TVG of a sheaf F is going to be by definition the following. So I take the projection onto the first factor of the pullback, this TV of F tensor with the pullback along the second factor of this G. So, for example, if G is like a, okay, so if I is like a set 1 up to n, and G is equal to the skyscraper sheaf at some point, then this TVG, okay, so this V in this case is sort of a tuple of representations, V1 up to Vn, and this is the composition in any order of TV1 x1 composed with TVN xn. And so in general, it's an integral, quote unquote, of such operators. Operators just meaning endofunctors. That's kind of what basically when I just say it only depends on the finite set, I've essentially quotiented by. You could do that, and it's not the thing I'm, okay, you want to, it's different and it's not what it's a slightly inconvenient way to do things. it's done in some literature on the subject, but it's.
So actually, xi is meant to be quotient by the simplification, or
No, it's just literally x to the I for me is just like the.
that's just the program.
It's just the product indexed by points of I. Yep. It's like, yeah. Okay, so what relations are there between these Hecke functors? So I was kind of pointing to some relations before, like, for example, well, this sort of tautology is kind of clear, and let me state this a little bit more in terms of commutative diagrams, and yeah. So so suppose I have a map from I to j, just a map of finite sets. So then, so basically the following diagram will commute. Or it's not really following. I'm going to go back to the start of the typewriter. Okay, so see, I'm saying it more formally than I said it here in my notes. Okay, so if I take, so suppose like, okay, what should you picture here? So what you should picture is the set 1, 2 mapping to 1, mapping to like a singleton. For example, so what you can do is you can take two representations and then sort of a sheaf just like on a single copy of x, which I'm going to think of as diagonally embedded. And so I can do two things out of this kind of construction. So one is I can form a sheaf on x to the I, and so here this is some kind of diagonal push forward. So so here this this f was a map from I to j, and that gives rise to a map from x to the j to x to the I. Yeah, like x to the j is all the maps from j into x. Or maybe I should call it delta f. So in the case over there, this is just like literally the diagonal copy of x sitting inside of the inside of x squared. So I can sort of take these two representations and maybe this sheaf at the diagonal, and then I can create a sheaf on this x to the I by a diagonal push forward. So it's sort of like sort of taking multiplicities of the points here. Or the other thing I can do is I can do, so this is like identity tensor like this. And the other thing I can do is I can apply the tensor structure along these factors. That's a j. And now both of these map to endofunctors on sheaves on Bun-G. And so this diagram commutes, and this sort of expresses the idea that I was saying before, that like if like if you do, maybe I didn't express it before. If you do the Hecke functor for v and then for w, and then you restrict to the diagonal, then you get the Hecke functor for v tensor w. So this expresses the idea that if you do this tv composed with tw, let me put the x's here, and then you restrict along the diagonal, and this is going to equal t of v tensor w is x. So now a definition is that, say, rep g check ron is the following category. So basically what I want to do is say, like, take a category which is kind of generated by these sorts of terms over various finite sets with these sorts of relations. And so the way we say that is with a co-limit of sheaves on, no, the other way around, representations. So there's some very formal thing you're supposed to say here. I take co-limits like this, where the data runs over maps of this sort. And this is, so formally, how am I on time? Oh, 3 minutes. OK. Formally, the index category is what's called the twisted arrow category of finite sets. And so here, this means that objects are just maps of finite sets, and morphisms. OK, I can never get the direction of the morphisms right, so I wrote it down. So morphisms, so if you have a map F1 to a J1, and you want to map this to a set from I2 to J2, these are the same things as commutative diagrams go from I1 to I2, J1, J2, where the map goes covariantly in the i's, and it goes contravariantly in the j's, which is the sort of behavior we were sort of seeing here. So there was some kind of like, well, this sort of felt contravariant because the direction changed. That's the, so you can imagine that as the j's, and this is sort of covariant in the i's. Maybe I've just expressed to myself how to remember the direction. OK, so that's what we have, and so that's basically that's a category. So I guess yeah, for like OK, this is some sort of monoidal category, and let me just briefly I'll leave that diagram up. Yes, exactly. So so this rep g check ron is a symmetric monoidal in some naive sense, or by some naive construction. And the sort of true Hecke symmetries state that this rep g check ron acts on this sheaves on bungee. So this is what I really have in mind by the Hecke action. This is the thing which recovers every other possible construction you could possibly give me. And it encodes sort of things like the way the commutativity constraint was constructed. It encodes many, many things. So if you ask me, if you give me something that might be a Hecke symmetry, it's encoded here, I claim. And this object the way it's more refined than my more naive notions is really important for the discussion that'll follow. So, okay, let me leave it there. Thanks.
Are there other questions?
Actually, question, yeah. For me, it looks like too much. There are a lot of things which left trivial function after scale. Because eventually, this be saturated in a number of points is equal to boundary, dimensional boundary.
Say again?
No, you don't need this very big powers of curves. You get essentially functors, all functors come from bounded height.
Yes. Yeah. So, and any or let me say it this way: there are very interesting Hecke functors that don't come from finite eyes. There are so like the great example is what's called the valence and spectral projector. This is sort of something which anyway, we can talk about it after. There are interesting Hecke functors that don't come from any finite eye and come from this whole category, but yeah. And everyth's built out of finite dimensional things. So
a lot of things are extreme in the answer. Is it true? That you get non-trivial object of this Girard which acts truly.
There exist such objects, but they have very global nature, I would say.
But I think it's a really huge ideal. We should work out.
So, you mean that?
This category it's like functions of larger number of variables. Yeah.
I think this will be addressed by the very next thing I'll say. So, but we'll do it tomorrow, I guess. Yeah. So it's again a very nice transition, but unfortunately my time's out.